the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed the logistic difference equations with two parameters, and after non-dimensionalization, we have reduced this equation to a parameter of a single one. So, in this lecture, we will discuss about analysis on logistic difference equations. This means that whatever this transformation we have just done for this two parameter values reducing to one parameter values, that analysis we will just do on logistic difference equations. Then we will just go for like periodically stable solutions, and in the last phase we will just go for the introduction of bifurcation. Since in the last lecture we have observed the nature of a logistic difference equation. This equation is represented in the form of xn plus 1 as r xn into 1 minus xn for different values of r, and we have just reduced to these parameters in a form that when we have just considered r as 2.5 after a peak variation, then we have like a stable solution. And when we have just considered these values r as 3.3, then a periodic oscillation we have just obtained with period 2 there. Also, if we have extended these values up to 3.33, then also we have got this periodic variation with period 2 there. But for the further extension of this value, when we have just considered this value as 3.9, we have just find a chaos there. And especially we have just used fixed point criterion for this stability region to find this one in a steady state form. For the steady state, we have just kept there lambda equals to 0, and the stability is existing when absolute value of r should be less than 1 there. And for the steady state of lambda equals to 1 minus 1 by r, stability condition is existing when r lies between 1 and 3 there. Especially we have just obtained this stability condition by putting this fixed function there. This means that x equals to f of x, we have just chosen to get this steady state solutions as lambda equals to 0 and lambda equals to 1 minus 1 by r. And when we have just go for this like graphical solutions, we have just find a iterative solution that except for r equals to 2.5, no other case showing the stability for these values. Since stability means we are just finding that the value remains constant, and after like so many times also there is no further change of these values, it has been find it out there. So, based on these results, so we are just going to analyze this difference equation stability conditions on different r values. So, beyond like r greater than 3, we observed some periodic oscillations in juxtapose of r approximately chosen as 3.3 and 3.33 with period 2 there. So, this means that very close neighborhoods we are just finding these oscillations as this period of 2 for this value of r equals to 3.3, and period 2 implies that successive generations will alternate between two different values of x, and let us call these values as zeta 1 and zeta 2. Since in the graphical sense, if you will just see there, so suddenly there is a oscillation of these values, suppose if it is just occurring, then after certain time you are just finding that there is a fixed variation of these values at like infinite time levels. And if you will just consider like the upper level value as zeta 1 there and the lower level value as zeta 2, then based on that values we can just find the stability of this formulation. So, especially if you will just go for this mathematical representation of this period 2, also called 2 point cycles. 2 point cycles means if initially we are just starting at a point, then finally we are just reaching at that point also. So, if we are just completing a cycle here, then finally we are just coming to the same point again. So, especially we have just obtained this difference equations in a oscillation form by putting this as xn plus 1 equals to f of xn, and if the periodicity is existing for 2 cycles, then we can just find xn plus 2 equals to xn. Since whatever the value we can just get at this point, finally we can just get this value at this point also. So, that is why we have just considered xn plus 2 equals to xm. And after combining these two equations, especially if you will just see here, xn plus 2 can be written as also, since xn plus 1 equals to f of xn here. So, xn plus 2 it can be written as f of xn plus 1, and which can be also written as, since we have known that xn plus 1 it can be written as f of xn. So, f of xn we can just write. So, that is why in a combined form we have just written xn plus 2 equals to f of xn plus 1 from the first statement, and if we are just using the second statement here, that is xn plus 1, this is nothing but f of xn there. So, finally, we are just obtaining this expression as f of xn. Let us call this function xn plus 2 as g of x here, which is represented in the form of f of x here, and the complete equation is xn plus 2 equals to g of xn here. So, if you will just go for like further analysis of this difference equation, so let suppose k we are just substituting as a new index which keeps every alternate value. This means that if we will just define k equals to n by 2 for every even n numbers. So, all the numbers if you will just define, and if you will just put k equals to n by 2, so finally we can just find this substitute values as n plus 2 by 2, which can be written as g of x of n by 2 here. But we are just considering only the even numbers here. So, that is why we are just writing it in a complete form as xk plus 1 equals to g of xk here. And the steady state solution of above equation zeta will be 2 periodic, since the first oscillation it starts and ends at the same point also after like 2 periods there. So, that is why we are just saying this solution of above equation zeta will be 2 periodic. Since zeta is oscillating between two different values, so it will have two significant solutions, and this will be like zeta 1 and zeta 2 we can just say. And with this one can easily analyze the stability of the above equation, which says that since we will have this equation xk plus 1 equals to g of xk, the stability condition can be achieved by differentiating first order sense to this function g of x here. So, that is why we are just writing here the absolute value of the first order difference of g of x at x equals to zeta should be less than 1. That is the stability condition we have just discussed in the previous lectures. And this condition is equivalent to, since we are just writing here as g of x as f of x here, and if you will just take this first order difference here, so then g dash x can be written as f dash of f of x into f dash x. So, here f of x is nothing but a fixed point function. So, that is why it is written as f of x equals to x. So, completely we can just write as f dash x at x equals to zeta 1 and f dash x at x equals to zeta 2. Since for the fixed point form, if you will just go for this application, the final reduction of this equation, this can be written as like f dash x at x equals to zeta 1, that is df by dx here, and then again df by dx at x equals to zeta 2, and since absolute value of dg by dx it should be less than 1. So, that is why we can just write absolute value of f dash x into f dash x at two different values of x, that is zeta 1 and zeta 2, the product should be less than 1 here in absolute sense. So, if you will just go for the further analysis of this logistic difference equation we have discussed in the last lecture, that f of x is chosen as r x into 1 minus x. So, g of x if you will just write, that is nothing but x is nothing but f of x here. So, that is why if you will just replace here r into x is replaced by f of x. So, that is why completely we can just write r x into 1 minus x in place of x, and then again 1 minus x, 1 minus into x is replaced by f of x here. So, if you will just take the complete product of this equation, then finally we can just obtain as r square x into 1 minus x into 1 minus r x plus r x square here. Hence, this difference equation we have just obtained for g of x is of interest, and where we can just obtain the solution using this 5.3 and 5.5. That is xk plus 1, it can be written as, since in the previous slide we have just written here xk plus 1, this is g of xk here. So, that is why xk plus 1 it can be written as like r square in place of x, we can just write xk here. So, r square xk into 1 minus xk into 1 minus Rxk plus Rx square here. And to obtain the steady state, we can just put here, since the fixed point values we are just using here. So, that is why we are just putting xk plus 1, this equals to xk, this equals to zeta here. And if you just put these values in the equation 5.6 here, then the algebraic equation will be reduced in the form of like, since xk plus 1 equals to zeta here and r square is still there. So, then xk is replaced by zeta here, then 1 minus xk is replaced again by zeta here, and 1 minus rxk plus rxk square, it can be written as 1 minus r zeta plus r zeta square. And if you will just take the difference of this left hand side and right hand side, we can just take common zeta from this equation. We can just write as zeta minus r square zeta into 1 minus zeta into 1 minus r zeta plus r zeta square here, this equals to 0. So, if you will just take common zeta, this can be written as zeta 1 minus r square 1 minus zeta into 1 minus r zeta plus r zeta square. So, especially either we can just consider zeta equals to 0 or rest of the expression this equals to 0 here. So, if you will just consider one steady state solution can be obtained if you will just consider zeta equals to 0 here, and others should be satisfied that 1 minus r square into 1 minus zeta into 1 minus r zeta plus r zeta square, this equals to 0. Obviously, this part will just give the representation as 1 equals to r square into 1 minus zeta into 1 minus r zeta plus r zeta square. So, this is especially a cubic equation and it is very difficult to obtain the solution. So, if you just go for this like a steady state of equation like xn plus 1 equals to f of xn, again we will just go for this fixed point functions here, and we can just obtain this steady state by using xn plus 2, which can be represented as f of xn. This simplifies this cubic equation to like a quadratic equation. So, especially if you just put here xn equals to xn plus 1 equals to xn plus 2 equals to zeta, then the reduced form of this equation for this can be written as like zeta equals to 1 minus 1 by r, we will just get if you will just put this non-zero steady state value of this equation xn plus 1 equals to r into xn into 1 minus xn. So, this zeta value will satisfy the cubic equation given in equation 5.8 here. But if we are just finding that zeta equals to 1 minus 1 by r is a solution here, if we will just take common of this root from this like cubic polynomial here, so that can be written as like zeta minus 1 plus 1 by r, and if you will just take common from this equation, then this equation will be reduced in the form of like zeta minus 1 plus 1 by r into zeta square minus zeta into 1 plus 1 by r plus 1 by r plus 1 by r square. So, even if you can just multiply this term, then you can just find this final solution as in the form of like here the cubic polynomial, whatever it has been written here. And sometimes also people can also divide these equations, or they can just take common to reduce this one in a quadratic form. Since a quadratic form, we can have a exact solution. And if you will just go for this like exact solution of this quadratic factor, so then this above reduced form of this equation can be written in a root form as zeta equals to r plus 1 plus or minus square root of r plus 1 into r minus 3 by 2r. So, if you just see here, r plus 1 means this should not be negative, and r minus 3 means this should not be negative to get the complete solution of zeta here. Neither it will be like imaginary function and we do not have any stability condition. So, that is why if you will just choose r less than minus 1 here, then we can just find the stability or any condition we can just obtain based on that values, or if you will just consider r greater than 3, then this root solution will have a positive value there itself. So, directly we can just find these roots from this equation here, and if we will just go for the like further calculated values of the steady states, which is defined for r less than minus 1 and r greater than 3 here to check the stability. So, if you will just use this equation like 5.4, that is f of x is given as like if you will just see f of x is written as r xn into 1 minus xn, or r x into 1 minus x. So, f of x is written as r x into 1 minus x. So, then if you just find the difference here, so f dash x it can be written as like r into 1 minus x plus r, this is r x and this is minus 1 here. So, this can be written as r into 1 minus x minus r x here. So, completely you can just get it as like r minus 2 r x here. So, if you just put x equals to zeta 1 here, then you can just find the solution, as since we have just obtained this zeta 1 values as like here r plus 1 plus or minus square root of r plus 1 into r minus 3 by 2 r. So, based on this you can just find df by dx at x equals to zeta 1 is this is the value. For plus value you can have a value like 2 roots, since we are just writing here zeta 1 and zeta 2. So, first root we can just consider as r plus 1 plus square root of r plus 1 into r minus 3 by 2 r, and second root we can just write as r plus 1 minus square root of r plus 1 into r minus 3 by 2 r. And if directly we will just put these values in case of f dash x here, then we can just obtain it as minus 1 minus square root of r plus 1 into r minus 3, and for x equals to zeta 2 if you will just put, then we can just obtain these values there. And after substituting equation 5.12 in 5.4, since we have just written there df by dx into df by dx at x equals to zeta 1 and x equals to zeta 2, then we can just obtain this is the quadratic equation. And especially if you will just take the fractionals here, then we cannot have a complete root here. So, that is why we have just defined the ranges, that for the stability we can just use that if r greater than 3 and r less than minus 1, then we can have satisfy this condition there. And this condition of stability for this equation is quietly satisfied if we are just assuming here r greater than 3 and r should be less than minus 1. And from this we can conclude that for positive values of r, since we are just considering only the positive values, so the steady state of 2 generation map, that is g of x is written as f of x here, which is existing only for r greater than 3 here. Since we are just considering only positive values of r, so that is why we are just taking r greater than 3 here. And this occurs only when steady state 1 minus 1 by r brings the stability, since we have just discussed this one in the previous slides also. And if we will just go for this upper limiting case, that is how far we can just go that we can just have a stable solution, since we are just assuming that r greater than 3, but we have to find a limiting point where it will have a different character or different nature, it will just exist. Since we have just to find that r equals to 3.9, we have a chaotic nature. So, that is why to find this range that where the stability condition can be achieved, we are just assuming that r should be lies between 3 and r1. r1 is a unknown parameter here. And if you will just go for a small numerical calculation of these values, so if you just assume r less than r1, then obviously we can just subtract both the sides minus 1 and we can just write this statement. And if you just do some manipulation, so finally we can just obtain this r1 value should satisfy 3 and 1 plus square root of 6 here. And especially we can just say that by substituting this in stability condition, the values of r1 will turn out to be r1 equals to 1 plus square root of 6, whose approximate value is 3.4494, and for that values, up to that values we can have a stable solution, and after that we do not know how the behavior of this function will just give you. So, if we will just go for analysis of these things, then we can just find one question, it will just come to the picture that what will happen beyond r value of 3.4494. So, the same has already been analyzed with a graph of iteration values for r equals to 3.9, since a chaotic nature we have just obtained for this r equals to 3.9 and found that it was a chaos. So, after 3.4494 for some values nature will be sometimes we can just get like 4 periodic, then 8 periodic, then after that how it is just behaving we cannot imagine. So, in general we can call it as chaos. Here we use the methodology to solve for 2 periodic solution. However, the same can be used for any values of n, but it is very cumbersome to solve for higher values of n. We have analyzed different scenarios of stable periodic oscillations with variations in parameter r, and there is a question arise that what will happen when parameter values will be perturbed. If a small parametric values will be added in the solution, then how it will just behave inside the system. And the phenomenon of analyzing significant changes in output with small perturbations in parameters is termed as bifurcation. Since if we are just finding this chaotic nature, this means that after certain oscillations you can just find that it may be like 4 periodic or 8 periodic, or we cannot imagine that how it is just behaving, then especially we are just saying it is chaos. But this bifurcations where it is starting, that is also important to note or to find it out. So, for this lecture we have discussed about the analysis of a logistic difference equation beyond r greater than 3. Since we have just find that there is a steady condition, it is just achieved for r equals to like 2.5, and when smoothly we have increased the values, then we have just find this oscillation starts, and r equals to like 3.3, we have just find that the oscillation starts with a period 2, and when we have just considered like 3.33, then we have just find that the same periodic nature it is observed. But for the further extension of these values, we do not know how it is just behaving. So, that is why we have just estimated this fixed point operations there, like in the form of x equals to f of x, and further we have just put this periodic oscillation condition, since after like the values of 3, it is just behaving erratically after certain points. So, that is why we have started to calculate these values for like different points, and for this different point ranges we have just considered this fixed point function, that is in the form of like x equals to f of x, and since this 2 period functions is existing there, so then we have just put it as xn plus 1 equals to like f of xn, and then xn plus 2 equals to xn, and based on that we have just find that this perturbation is existing up to certain points, and after that we are just finding this behaves erratically. And we have also obtained this periodic stable solution up to certain level that we have discussed. Then we have just discussed about this bifurcation, since the point at which this deviation or this chaotic behavior starts, especially that point it is very important to compute or to calculate that one. So, thank you for listening this lecture.